Welcome back for the lesson 3.5 video. This video is over complex numbers. It's going to feel like we went off in a different direction, but we have to do that for a particular purpose, and you'll see why later. So we're going to introduce what a complex number is in this lesson, how to perform some arithmetic operations on those complex numbers, also how to find complex zeros of a quadratic equation, and to find complex solutions of a quadratic equation. So first of all, an imaginary number. So an imaginary number, I, is defined as the square root of a -1. And I squared is just a -1. Numbers of the form BI, where B is a real number, are called pure imaginary numbers. So let's practice writing some pure imaginary numbers. The square root of a -25, which we've never been able to do before, because it's not real, it's imaginary, can be broken into these two pieces. And the square root of a -1 is I, and the square root of 25 is 5. And we always write the number, the real number coefficient out in front of the I. So the square root of a -108. So we are looking for some real number, a real factor of 108 that could be a perfect square root. And that could be the square root of a -1 times the square root of 36 times the square root of 3. And I just looked for factors of 108 that were perfect square roots, and 36 is one of them. So that gives us, this is I, this is 6, and that stays the square root of 3. So this actually simplifies as 6I, the square root of 3. So the real portion comes out in front, and the I goes in front of the radical. The square root of a -4 over 9. So this can be broken into the square root of a -1 times the square root of 4 over 9. And that is I. And then we can break that apart into the square root of 4 over the square root of 9. And both of those simplify. So that's the I times the square root, or times 2 over 3. And we're going to actually write that as 2/3 I. Now, within pure imaginary numbers, we can send that to something called a complex number. A complex number is a number of the form A plus BI, where A and B are real numbers. So the A is the real part of the complex number, and B is the pure imaginary part. So let's practice writing some of these. We have the cubed root of 5, and that is simply the cubed root of 5, because there is no imaginary part. And this, I really think I wanted that to say I, the -I plus the square root of 2. And so this is the square root of 2 plus a -I, or you could just say the square root of 2 minus I, where the square root of 2 is the real part and I is the imaginary part. And then we have C is I over 1 over 4. And so there is no real part. There is only the imaginary, and that's really 1/4 I. Now, example 3 has us breaking apart and telling what are the real and imaginary parts. So the real, I'm going to list those for each of the 3, and the imaginary for each of the 3. So this is the real part, the -2, and then the 3i is the imaginary. And then the 4 is the real here, and then -i is the imaginary. And then the negative square root of 3 is the real, and then there is no imaginary on this one. We can add and subtract complex numbers. So it's similar to just adding and subtracting like terms. So we can regroup these. So we've got 3 minus 4 plus 2i plus I. And so adding the real numbers, we get a -1 plus 3i. And then here we have only just the -2 plus I, because that's all that's there. And then here we have a square root of 3 and a minus square root of 3. So those cancel each other out and we just have I. We can also multiply complex numbers. And so we're going to multiply the two terms times the two terms. And so we will use our FOIL, our first, outside, inside, and last concept. So a -3 times 5 is a -15. And then a -3 times a -2i is a positive 6i. And then we have a positive 20i from the insides. And then the two imaginary pieces get multiplied to make a -8i squared. Then, of course, we can combine our like terms in the middle. So we have a -15 plus 26i minus 8i squared. But if we recall, I squared equals a -1. So we'll never end up with an I squared ever when we simplify, because that's I squared becomes a -1. So we have a -15 plus 26i minus 8 times a -1 when we replace the I squared. So this term becomes a part of the real number. So a -15 plus 26i plus 8. And then we can combine a -15 is 8. So we have a -7 plus 26i. So that's the unique piece. When two complex numbers get multiplied, we always end up with just a complex number. Now, we can also have division of complex numbers. But we have division of complex numbers, we have to learn about a complex conjugate. The complex conjugate of a complex number, a plus bi, is given by a minus bi. The complex conjugate of a complex number has the same real part as the original number, but the negative of the imaginary part. So a plus bi and a minus bi. So it says find the complex conjugate of the following numbers. So this will just be 1 minus 2i. And this will just be plus 3i, and that will just be 2 because there's no imaginary part. So let's see what it looks like to multiply conjugates together. Remember when we learned how to multiply just regular conjugates together, x minus 2 and x plus 2, what happens is the middle two terms cancel out, and we end up with a difference of 2 squares. Because it's x squared minus 2x plus 2x minus 4, canceling out those two middle terms. So something similar is going to happen here. We have a -3 minus 7i times a -3 plus 7i. So we'll have a -3 times -3 is a positive 9. A -3 times a positive 7i is a minus 21i. And then we have a plus 21i. And then our last two terms make a -49i squared. So similar as a regular conjugate, these complex conjugates also cancel out the middle terms. And we have 9 subtracting 49. The I squared, remember, gets replaced with a -1. And so this simplifies to 9 plus 49 or 58. I'll be expecting you to show all of your work on these too. In the notes, in the homework, as well as on the test and quiz. So finally, we're going to divide by a complex number. So the reason we had to learn about complex conjugates is because we cannot have a complex number in the denominator of a fraction. So we are going to multiply by the conjugate, the complex conjugate, to get rid of that, because notice that when we multiply complex conjugates, we end up with only a real number. That's the benefit of multiplying by the conjugate. So we're going to multiply by that -3 plus 7i, and we have to do the same on top. And we already know the bottom simplifies to 58 because that's exactly what we did up here. So we get 58 in the denominator. And then the numerator gets multiplied. Distributing that 4, we have a -12 plus 28i. And it is okay to have a complex number in the numerator. Use the definition of I to solve the equation x squared equals -9. So if we were going to solve for x, we would take the square root of both sides. And the square root of, x squared is x. And now we know that we can separate these. And this will be, the square root of 9 is 3, and the square root of a -1 is I. And we have to remember that it is plus and minus. There are two roots there, a plus and a minus. Computing the zeros for this function uses zeros to find the x-intercepts. Okay, so I'm going to use the quadratic equation where a is a -3, b is 2, and c is a -1. So my x-intercepts are going to be opposite of b, so a -2 plus or minus the square root of b squared minus 4 times a times c all over 2a. So a -2 plus or minus the square root of 4, and then we have 3 negatives, so it becomes a -12 over a -6. So -2 plus or minus the square root of a -8 over a -6. And this negative square root of -8, we just have to remember that square root of 8 is the same as the square root of 4 times the square root of 2. So that becomes 2 times the square root of 2. I don't want a decimal answer. I want you to leave it in radical form to be correct. So we have a -2 plus or minus 2i times the square root of 2, because that was a negative, square root of a -8, all over a -6. And then to simplify this, we have to be able to, if we're going to cancel something out, it has to cancel out of the real part, the complex part, and the denominator. And it looks like we can only do a 2. So we have a -1, and actually the negatives cancel. So it's a +1 plus or minus I times the square root of 2 over 3. And those are the x-intercepts. We could have tried to factor, but it wouldn't have worked. So the x-intercepts are these comma zeros, and then these are the zeros. So kind of going back to what we learned at the beginning of chapter 3, I love putting it all together. You know that because a is negative, it's face down. And my x-intercepts, there's going to be a positive one. And it looks like they might both be on this side or so. But remember, because it's face down and these are imaginary, it's never going to touch. And so we can see our y-intercept is at 0, 0, -1. So 0 and a -1. So it's going to come up and then go down, but it'll never touch. And that's why they're imaginary zeros. Example 9 says, Find all the solutions of the quadratic equation. So again, we're going to list out A is a -2, B is 3, and C is a -2. So we have the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2A. And that leaves us with a -3 plus or minus the square root of 9, and we have negative, negative, negative. So it's a -16 over a -4. So this is a -3 plus or minus the square root of a -7 over a -4. And 7 is irrational, but we can pull out the I. So we have a -3 over -4 is just that cancels. So it's 3 plus or minus I times the square root of 7 over 4. And that is why we needed to know about complex numbers, because when we find the x-intercepts of a parabola or any polynomial that does not come down and cross the x-axis, we have imaginary zeros. Catch me back for another video.